All right, let's have a look at proof and inequalities. Just a reminder of the different types of proofs that we have. We have our deductive proofs, which I guess we most commonly see with geometry, and that's where we have known facts. And so we write down facts, and then from that we deduce and come up with a conclusion. Then, of course, we've seen inductive proofs, and that's where we assume what it is we're trying to prove, and then from there induce the solution. The other one we don't see that often, but proof by contradiction. You might remember we had a look at that one last year when we proved, what was it, I think it was square root of 2 was irrational, something like that. And that's where we actually assume the opposite of what we're trying to prove. And then throughout our proof, we come up to something that's wrong or contradicts our original assumption. And so therefore we conclude, well, hang on, therefore my original statement must be false. And then the opposite, therefore, could be true. Let's have a look at this in context with inequality, some different techniques of how to solve inequality questions. One of the more common ideas is this. If I'm trying to prove x is greater than or equal to y, then it's often easier to prove x minus y is greater than or equal to 0. Because showing something is always positive or something is always negative can be a lot easier. And once we have that fact that x minus y is greater than or equal to 0, we can then move terms. I mean, you can move terms in facts, but we have to prove it to be a fact first. So if I wanted to prove PQ is less than or equal to P squared plus Q squared on 2, quite an old question and quite a simple little question. But if I use that technique, I go, okay, what I'm going to do is I'm going to try and show this algebraic expression, and that's all it is at the moment, but I'm going to show it's always positive in this case. And so if I turn it into one fraction, you can see it comes out quite easily, because the top now we can factorise to be a perfect square, and of course we know perfect squares are always greater than or equal to 0. So I now know that is a fact. It is a fact that P squared plus Q squared on 2 minus PQ is greater than or equal to 0. So I can move terms and rearrange the expression, so therefore it must be true that P squared plus Q squared on 2 is greater than or equal to P. Another way I could do this, if I use the proof by contradiction idea, it's an unusual way of doing it, but just to show you how it would, well, I would assume the opposite is true. I'm going to assume that PQ is greater than P squared plus Q squared on 2. Now, I've assumed that to be true, so if I manipulate it, that would mean 2PQ is greater than P squared plus Q squared. And if that's true, then 0 would be greater than P squared minus 2PQ plus Q squared, which means 0 would be greater than P minus Q squared, which of course is not true, because we know that P minus Q squared is always greater than or equal to 0. So we have a contradiction. Therefore, my original assumption must have been false. So PQ must indeed be less than or equal to P squared plus Q squared on 2. It's an unusual way of doing it, but I mean, I could do it by using that idea. Okay, let's have a look at this question. A squared plus B squared plus C squared is always greater than AB plus BC plus AC. For this one, I'm going to start with a known fact. And the fact that I'm going to start with is, again, that I know a perfect square is greater than 0. So A minus B squared is greater than 0. If I expand out the left-hand side, again, I know this to be true, so I can move terms. So it must be true to say A squared plus B squared is greater than 2AB. A and B are just pronumerals. I could have put any letters there. So I could have said A squared plus C squared is greater than 2AC. I could have said B squared plus C squared is greater than 2BC. And if I add the three together, I end up with 2A squared plus 2B squared plus 2C squared is greater than 2AB plus 2AC plus 2BC. Divide both sides by 2, and I have my proof. Now, if A plus B plus C is equal to 1, we're going to prove that AB plus AC plus BC is less than a third. I'm just going to, an expression here, we've seen it very often. It's the same as saying the sum of the roots squared 1 at a time is equal to the sum of the roots 1 at a time squared minus 2. Same sort of idea. And the reason I'm going to do that is because I'm now going to play around with this inequality that we just proved. Right? So it therefore must be true that A plus B plus C all squared minus 2ab plus ac plus bc is greater than ab plus ac plus bc. Okay? Because we just said a squared plus b squared plus c squared is equal to that. So I'm just replacing it. So if I move it around, I could say, well, hang on. So 3ab plus ac plus bc is less than a plus b plus c all squared. So 3 lots of a plus b, because remember, a plus b plus c is equal to 1. So 3 lots of ab plus ac plus bc is less than 1. Divide both sides by 3. We have the result that they wish. Then they've asked me to do this. Prove that a third of a plus b plus c is greater than or equal to 3 times the square root of abc. Again, we proved a squared plus b squared plus c squared is greater than or equal to ab plus ac plus bc. Okay. If I move to the left-hand side, because remember we've proven it, it's now a known fact, so I can move terms around and it'll still be true. So a squared plus b squared plus c squared minus ab minus ac minus bc must be greater than or equal to 0. I'm going to multiply that by a plus b plus c. I think, well, that's a curious thing to do. The reason I'm doing that is because I know I'm going to end up with cube roots. So cubes are in there, but in this case, the highest power I've got is squares. So if I multiply by a plus b plus c, that will create an a cubed, a b cubed, and a c cubed. It'll create a lot of other terms as well. In fact, it'll create all those terms. Okay? But if you look very closely, something nice happens. Yeah, there's a lot of cancelling that happens in there. I actually end up with just that. A cubed plus b cubed plus c cubed minus 3abc is greater than or equal to 0. So I now know 1/3 of a cubed plus b cubed plus c cubed is greater than or equal to abc. So very close to what I want, but not quite what I want. But hey, a and b and c are just pronumerals, which were defined to just be positive numbers, if I remember correctly. So I'm going to say a is the cube root of a, and b is the cube root of b, and c is the cube root of c. If I substitute that in, I get 1/3 of a plus b plus c is greater than the cube root of abc. A is just representing a number. The cube root of a is a number. A can be any number. We're just saying if you get any 3 numbers, add them together and cube them, you get that. Okay, the 3 numbers I have chosen to use are the cube root of a, the cube root of b, and the cube root of c. This brings up a really interesting result. This idea of what we've just proven basically is the arithmetic mean is always greater than or equal to the geometric mean. Now, arithmetic mean is what you understand to be mean. We use it in stats. It's average. But its correct term is not mean. Its correct term is arithmetic mean, because it's to do with arithmetic series where you add all the terms. There is also a geometric mean where you multiply all the terms and find the nth root of it. And it is always true. You can quote that. Now, I couldn't quote it in the one where I had to prove it, of course. So if they are asking you to prove that result, you can't quote it. But otherwise, you can always use this idea, and it's a very useful idea in a lot of these inequality questions. Here's part D to the same question now. Suppose that, as you would, 1 plus x times 1 plus y plus 1 plus z is equal to 8. We're now going to prove x, y, z is less than or equal to 1. Going to do it 2 ways. First way is a lot of fun. Well, what is 1 plus x plus 1 times 1 plus y plus 1 plus z? I thought, well, let's expand the whole thing out. So I now know this expression is equal to 8. But, using what we just proved, 1/3 of x plus y plus z is always greater than or equal to the cube root of x, y, z. Arithmetic mean, always greater than or equal to the geometric mean. So x plus y plus z will always be greater than or equal to 3 times the cube root of x, y, z. Now that's true for any 3 pronumerals. I just happen to have used x, y, and z. I could have used xy as one pronumeral, yz as one prime numeral, and xz as one prime numeral. And so, therefore, those three things added together would be greater than or equal to 3 times the cube root of those three things multiplied together. And multiplied together, they would become x squared, y squared, z squared. Okay? So I now have that inequality. Okay? So I now know, just playing around with the indices there, I've made it the cube root of x, y, z all squared. Now remember, we know that 1 plus x plus y plus all this is equal to 8. Okay? So therefore, if x plus y plus z is greater than 3 times the cube root of x, y, z, and x, y, x, z, y, z is greater than or equal to that, then this expression must be less than or equal to 8. But have a look at that expression there. 1, 3, 3, 1. Powers of the root x, y, z. 0, 1, 2, 3. Oh! What do you know? Just to highlight it in case you haven't seen it. Remember, I could have written that last term as the cube root of x, y, z all cubed. And so what I've actually got is 1 plus the cube root of x, y, z all cubed is less than or equal to 8. Well, in that case, 1 plus the cube root of x, y, z must be less than or equal to 2, which means the cube root of x, y, z is less than or equal to 1, which means x, y, z must be less than or equal to 1. Proven. I show you that because I really like it. It's probably not the best way of doing it. Have a look at this one. This is neater. Instead of, remember, I expanded the whole thing out. Remember, we had 1 plus x times 1 plus y plus 1 plus z. So well, let's just look at the individual piece. And again, using the idea of arithmetic mean greater than or equal to geometric mean. 1 plus x, so two things added together, must be greater than or equal to 2 times the square root of those two things multiplied together. Next times 1 is x. And I could do that with the 1 plus y, and I could do that with the 1 plus z. Remember, x, y, z, they're all positive numbers here. So if I multiply those three things together, it must be greater than when I multiply 2 root x times 2 root y, so, which is 8 times the square root of x, y, z. So 8, because we said 1 plus x times 1 plus y was equal to 8. And so 1 is greater than or equal to 1 times the square root of x, y, z. Square root of x, y, z plus. That might be a little bit quicker than the other, but I really like the other one. And so x, y, z is less than or equal to 1.
So can you just quote a
Yes, you can. Unless it is the inequality that they've asked you to prove, then okay, you've got to prove it.
But you always can write it.
But otherwise you could write, yeah, A, arithmetic mean greater than or equal to geometric mean. Yep. All right, let's have a look at some more interesting ones. Have a look at some. We're going to prove that 2 over a plus b plus 2 over b plus c plus 2 over a plus c is in between 9 on a plus b plus c and 1 on a plus 1 on b plus 1 on c. So I'm going to do it using arithmetic mean, geometric mean again. If I had a plus b times 1 on a plus 1 on b, two things multiplied together, right? Two things added together must be greater than. So the a plus b greater than or equal to 2 root ab. The 1 on a plus the 1 on b is greater than 2 on 1 root 1 on ab. But the root ab's now cancel, and I get that a plus b times 1 on a plus 1 on b is equal to 4. Okay? So therefore, if I rearrange that now, I know 1 on a plus 1 on b is greater than or equal to 4 on a plus b. But again, a and b, they're just letters. I could have done that for any of them. So therefore, 1 on b plus 1 on c was greater than or equal to 4 on b plus c. And 1 on a plus 1 on c is greater than or equal to 4 on a plus c. If I add that up, I get 2 on a plus 2 on b plus 2 on c greater than or equal to 4 on a plus b plus 4 on b plus c. Divide both sides by 2, and we have half of what we want. Okay? Yeah?
When you say it's equal to 4,
Yes?
isn't it greater or equal to 4?
No, I'm saying this line is equal to 4, therefore this is greater than or equal to.
Oh.
Now, I'm going to do it again, but this time, I've now got a fraction here with 3 terms in it. So I'm going to say a plus b plus c is greater than or equal to 3 times the cube root of abc. And similarly, 1 on a plus 1 on b plus 1 on c is greater than or equal to 3 times the cube root of 1 on abc, which cancels to give me 9. So therefore, 1 on a plus 1 on b plus 1 on c must be greater than or equal to 9 on a plus b plus c. So it certainly proves that 1 plus there is greater than 9 on a plus b. Well, what about the bit in the middle? I haven't proven that it's greater than that. Well, I'm just going to replace some things. A could have been anything. So how about I replace a with a plus b with b plus c, and c with a plus c, and then you get, on the left-hand side, you get 1 on a plus b, plus 1 on b plus c, plus 1 on c, and on the right-hand side, you now get 9 on 2 lots of a plus b plus c. Oh, well, let's multiply both sides by 2. Oh, good, now I've got that bit is, in fact, bigger than the 9 on a plus b plus c. Okay? But each time, all I'm using is the idea, arithmetic mean greater than geometric mean. And so there we go. We've trapped it in the middle of those 2 inequalities. I thought it would be fun to have a look at the one that was in yesterday's test. Because, of course, yesterday we didn't know how to do it. All right? Well, this part is just arithmetic mean greater than geometric mean. 2 things added together will always be greater than 2 things, 2 times the square root. But, right? There's only one but. So a plus 1 on a is greater than or equal to 2 times the square root of a times 1 on a. Oh, a times 1 on a, that's 1. So, there we go. A plus 1 on a is greater than or equal to 2. But, of course, you didn't know that. So, the very simple way of doing it, and this is how you would, if you have to prove arithmetic mean. So I was tossing up, is this question actually asking me to prove arithmetic mean is greater than or equal to geometric mean? And the way you do it is always with a perfect square. Okay? But you make the perfect square so that you know when you square it, you've got to get those 2 terms. So the 2 things I want is root a and 1 on root a, and you've got to make the middle term minus because you're going to move it to the other side. You see? So I know that's always greater than or equal to 0. So when I square it, I'll get a minus 2 plus 1 on a is greater than or equal to 0. And I can move the 2 to the other side. And I've got the result. Okay. The second part was a little bit more interesting. We now had to show that. Remember, we now know a plus 1 on a is greater than or equal to 2. Well, if a plus 1 on a is greater than 2, then b on a plus a on b must be greater than or equal to 2. Because we're saying a number plus its reciprocal is greater than or equal to 2. And it must be true then that c on a plus a on c is greater than or equal to 2, and c on b plus b on c is greater than or equal to 2. Add them together. Oh, that should be a 6, shouldn't it? Whoops. It was a 6 in the next line. 2 plus 2 plus 2 is 6, by the way, not 2. And there it is. We have it. Third part of the question then. Show that a on b plus c. Jeez. Okay. We've just proven that. Oh, gee, that's close, isn't it? One's upside down. I know. How about I change? Well, because look, bottom of the fraction is not a, but it's b plus c. So I'll make it b plus c. So everywhere I see an a in this thing, I'm going to replace it with b plus c. Everywhere I see a b, I'm going to replace it with a plus c. And everywhere I see a c, I'm going to replace it with a plus b. And we end up with that. Now have a look at the fraction. The top of the fraction here, I've got 2a plus c plus b on b plus... Oh, that's just 1 plus 2a on b plus c. And the other one's just 1 plus 2b on a plus c. And the other one's 1 plus 2c. So that means that 2a on b plus c plus 2b on a plus c plus 2c... Divided by 2. And there's our answer.
We're going to do it with everything now.
All right. So in the handouts, there's a few things in there. There's 10 Ds in our textbook, of course. Cambridge 8H. There's just one question in there, which is interesting. That's the real one, by the way. There's the inequality sheets. There's a few that I've found over the years that I put in there, and I think they've got solutions, those ones, so they're not too bad. I don't even remember if I did put in the pretend Cambridge or not. They might be there. So